something goes wrong here.
There
this
it is.
one.
Yeah, it is
Okay, this blank. And
so it.
this one. And this one.
That's it.
Okay.
Okay.
Yeah, so good afternoon, everybody, and welcome to the second of my two lectures. So if I remember correctly, if not, you will correct me, we stopped at this slide. So it shows that actually critical surface separating normal from superconducting state can be quite strongly expanded if we use nanostructuring in order to confine and to localize quantized vortices and superconductors. And in some of my previous picture, I was maybe a bit optimistic. I also put here a dashed line that critical temperature, the zero temperature, can be enhanced by using nanostructuring. Probably it is so, but nobody knows how to do it. So basically, to increase TC through nanostructuring, this is completely terra incognita, and it doesn't work that easy, like, for example, with enhancing critical current and enhancing critical magnetic fields. So, vortex in a superconductor represents a very remarkable object, which is characterized by depression of density of Cooper pairs. So this is n density of superconducting Cooper pairs, and at the location of a vortex, this must go to zero and then coming back again. And the depression is relatively narrow. It's determined, the width of this depression, although the parameter is determined by 2 times coherence length. On the other hand, now you suppress superconducting state, and it becomes much easier for magnetic field to penetrate at the location where all the parameter is suppressed. And therefore here you have enhanced local field. And local field penetrates in the form of quantized vortices, and characteristic size of that is 2 times lambda. And as you know, Ginzburg-Landau parameter is just the ratio of these two. You can also calculate critical current, and then it circulates nicely around this vortex, and intensity dies out as we are moving away from the so-called vortex core. And as I already mentioned, the key issue here in vortices for physics of vortices in quantum systems was this problem of can we have finite L, because superfluid velocity is quantum number L, and inversely proportional also to distance from the location to the circulating current. And it's clearly seen that this ratio is divergent for R going to zero, and therefore many people thought that the only way for quantum systems to survive is to keep L equals to zero, and then you have a Meissner state, and that's it, the story is over. And if you take an infinite cylinder of type 1 superconductor, this is indeed the only possible situation. On the other hand, before the Second World War in the 30s, Onsager noticed that actually this is not completely correct, but in quantum systems it should be weighed also with square of the modulus of your other parameter. And if you have problems with R going to zero, then you can solve this problem by allowing here your order parameter going to zero. And then you have 0 divided by 0, no problem. So then this is no catastrophe for these quantum systems. And that concept of vortex was designed by Onsager and then advertised a lot and also applied to superfluid helium by Feynman. And then Landau read about this in one of preprints by Feynman, and then he called up Abrikosov, who was one of the youngest collaborators in his team, and he said, why don't we do it for superconductors? And Abrikosov actually said that actually this has been done already time ago, so in 53, and that was already the year 57, and the manuscript was still in the drawer of important papers which were buried by Landau, and then he extracted it, read and liked it very much, and it was quickly published. And that paper was written by Alexei Abrikosov, and we invited him to our Vortex 3 conference. It was in Rhodes, in Crete in 2003, and I think 2 weeks or 10 days after this picture was taken, it was announced that he was awarded Nobel Prize for his pioneering work in the field of theory of superconductivity. And that's probably why he has this enigmatic smile on his face. So I have suspicion that he knew it already from some sources. So, because normally he's rather skeptical and extremely critical person. So I wrote with him as an editor 2 review papers for advances in physics in '84, and then on his request, and then I brought manuscript of the first one to him, and then he invited me to, it was meeting at his apartment, and he invited me to take a seat. He said, Victor, you'd better sit because I have to tell you something. I said, okay, this doesn't sound very good. And he started, it's very bad review paper, he said. I said, okay, which journal should I submit it now next? And then he started discussions, so this, and it turned out that criticisms were reduced to maybe 4 lines or 5 lines, and the rest was very positive. So I was, in the end, pleasantly surprised. And then this was published in '84 in Advances in Physics, on not on subject of superconductivity, but on concentrated Kondo systems, on heavy fermion systems. And second review paper, again on his request, I've written in the same year, '84, and that was at that time called semi-magnetic semiconductors. By now, this is called just magnetic semiconductors, and that both papers are, I'm happy, quite popular even now. All right, so he was very here optimistic, and probably because of that, and we enjoyed his, and he criticized me that there was no special session because it was 2003, and you see it's exactly 50 years after his theoretical prediction of type 2 superconductivity and vortex state. And then he asked me then, Victor, why didn't you organize a special session? 50 years of type 2 superconductivity. I said, wait a second, Alexei Alexeyevich, you published in '57. If I'm good in calculus, we should wait still another 4 years to celebrate that 50 years. He said, oh, no, Victor. And then he told me this story. So that's by now very well known. Now I'm going to proceed now with a lot of experimental data on visualizing these abricosal vortices with the help of a rather interesting technique, which is scanning whole probe microscopy, which was very briefly mentioned by Dima Rodichev in his overview of different scanning techniques. And the core and the heart of this device is this corner, which is metallized. So this metallization is playing the role of very cheap STM tip. So it doesn't look like a tip, right? But you navigate this corner to close proximity to your sample. And here you see 2-dimensional electron gas, high mobility. And here you see whole cross. And this whole cross has typical dimensions here, maybe 1/3 of micron, but there is also depletion of density of 2D gas at the edges, so real size of whole cross is smaller. And then you use powerful technique like any scanning probe, also discussed yesterday a lot, and then you can scan and you can measure local magnetic fields quite nicely, and you can have a map, precise map of local magnetic fields at the top of a superconducting material. So then you put it in a superconducting solenoid, and then normally you put there 2 samples. One is typical type 2 superconductor, just to calibrate your system, and next to it you put the sample you want to investigate. All right, so how it works, you take this niobium diselenide, and then you measure different vortex patterns at different magnetic fields, and then you plot the data, and they nicely follow the expected spacing, which is 1 divided by square root of applied magnetic field, 1 of square root of B, and then you see basically what is expected for type 2 superconductor. And this is a very good calibration of your setup. And then the next thing is about so-called the use of scanning whole probe spectroscopy to investigate vortex patterns in these so-called type 1.5 superconductors. So certainly you know what is type 1 superconductor, certainly you know what is type 2 superconductor. The question is what is type 1.5? And for that you need a two-band material. And then basically in some materials a very unique situation is possible. So one band may be responsible for attempting to produce superconductivity of type 2, and another subband is attempting to produce superconductivity of the first type, type 1. Of course, you have coupling between these two different gaps in case of formation of Cooper pairs. But if this coupling is not very strong, then this thing is still feasible to observe. And then you can also model this MGB2 sample. I'm already a little bit anticipating in which material you can see it. And then you can see neither type 1 behavior nor type 2, but something in between. And theoretically, it was predicted by Yegor Babayev, and then further on elaborated by him with his colleagues. And they predicted that basically in certain materials, if you have a multi-band superconductor, and if one band attempts to be in type 1 state, another one in type 2, then you can have a unique situation, which is called type 1.5. So to summarize, if you have a single band or single component superconductors, so they are typically either type 1, lambda over xi less than 1 over square root of 2, with pure attractive vortex-vortex interaction, or they are type 2, lambda over xi is bigger than 1 over square root of 2, where you have pure repulsive vortex-vortex interaction. So in type 1 you have Meissner state and you have normal state separated by this line. In type 2 you have here mixed state separating Meissner from normal. So this you know pretty well. And as predicted by Babayev and Spite in 2005, and we made experiments in 2009, then if you have a two-gap material where you should first introduce two wave function, two other parameters for one subband and for another, and introduce coupling between them, then you may have a unique situation when both conditions are simultaneously fulfilled. So one subband will be in type 1 regime, while another may be in type 2. And then actually what happens is that you have Meissner state close to HC2, you still have conventional Abrikosov mixed state, but here you see some interesting effect. You have vortex clusters and vortex stripes separated by areas which are vortex free. So this reminds you the following situation. If you take type 1 superconductor in an intermediate state, then you have stripes of superconducting areas, normal areas, superconducting normal, superconducting normal. And then you deposit on top of that type 2 superconductor. Then the area here where vortices penetrate, then here on top of type 2 superconducting film you will see a lot of vortices. Here you will see none. A lot of vortices and none. So that's why you may expect these stripes to appear. So if you actually then also consider vortex-vortex interaction, then you have competition between short-range repulsion and long-range interaction, and this will be eventually responsible for this very peculiar interaction force between vortices in these so-called type 1.5 materials. So, yes?
The phase diagram, this transition, the line, is a true phase transition or just a crossover?
This is crossover. This is crossover. And it's also rather sensitive to demagnetizing fields, and you need actually, so we did it on MGB2, so I'll come to that later on. You need really very clean MGB2. If your MGB2 is thin film or not very clean single crystal, you enter into regime when both subbands are in type 2 regime. So basically then you lose this one completely. So then, as we have already seen from presentation by Dima Rodichev, that if you take MGB2, then you have here clear in tunneling spectra clear two-band features, and this actually enables you to have sigma band of the order of 7.1 milli-electron volt and pi band of the order of 2.2 milli-electron volt. And if a sample is clean, then this leads to Xi related to sigma band 13 nanometers and lambda related to sigma band 48 nanometers. And Xi pi band is 51 nanometer and lambda pi is 34. So you have already suspicion that this one is possibly in type 1 regime. And this one is clearly in type 2. So this is a good candidate for observing type 1.5 behavior. But of course, I have to repeat again that you have to be very careful with quality of crystal. If you reduce mean free path, then as you know, these materials type 1 become automatically type 2. So and then we were always measuring in the same run for reference niobium deselenide, abricosov vortex lattice, and then surprise, surprise, you have domains vortex free and domains where you have a lot of vortices vortex rich. And then you increase magnetic field. Here vortices are coming closer to each other, but here you see this semi-Meissner area which cannot be populated by vortices, and here the features typical for type 1 superconductivity are dominant in fact. And then you can consider here this evolution of these patterns in different magnetic field, and then it's very persistent and fully reproducible pattern, and then actually you can analyze this.
Victor, sorry,
yes.
Sorry. This is, did you heat and cool down again?
Yeah, always, always. Apply field, and in the field, cool down. And then below TC, you scan. Because so if you want to change field, then again, you warm up, apply higher field, cool down, and scan again.
But this is a kind of a frozen pattern because it's a very, very small field, right? So
it's in a very small field, yeah, but the crystal is actually quite thin, so you have to enhance effective field by taking into account demagnetizing fields. Yeah.
Does it fix to the crystal?
It's for single crystal only. So if I take in the same experiment thin film, MgB2, or dirty crystal, then I see more or less exactly this one.
Is that fixed to the crystal, this pattern?
What do you mean fixed to the crystal? If I apply magnetic field, a different field, then the vortex pattern is changed accordingly.
Yeah, but you get same way like this?
Ah, you mean directional stripes?
Yeah.
In most cases, it's the same. Yes.
So it's fixed to somehow to the crystal?
Could be fixed to crystal, but if you take the same piece from the same batch, it can be. There is no evident way to, let's say, to bind it to some imperfections or whatever in the crystal, which are going in some preferential direction. I don't think so.
Okay.
Okay, so that was actually that point on type 1.5, and then you can analyze the evolution of these patterns with magnetic field. This is what you expect for vortex in type 2 distance, and then what we have observed here. Then inside these stripes, you have practically not very strongly different vortex distances, but you have more and more stripes instead as a function of stronger magnetic field. Then you can put here also old data, what were obtained before with scanning squid, and also with magnetic decoration, and it fits actually quite well on the same plot. So basically the observed features cannot be explained in any case by type 2 behavior, and can be nicely explained if you assume indeed that you have two subbands in different regime for your superconductivity. So one subband generates type 1, another one generates type 2, and then these subbands are coupled, and if you increase coupling, then basically theory tells you that for strong coupling it doesn't matter. Initial subbands can be type 1, type 2, but in the end you will get a homogeneous solution and not something like what we have seen before, which is typical for relatively weak mixing between the bands. All right, so that's the first piece of my second part. So type 1.5 can be seen in clean MgB2, but also first experiments on these S1, S2 hybrids show exactly similar behavior. And basically what you do, you have stripes intermediate state with stripes, normal, superconducting normal, and then you put thin insulating layer, and on top you put type 2 superconductor, and type 2 superconductor helps you to decorate these stripes. Yes?
It high enough magnetic field. Could you get
yes.
under abricos?
Yes. If you increase magnetic field closer to HC2, you recover always triangular lattice. Always. Okay, so now, so what was it? So squid microscopy, scanning hole probe, beta decoration, and modeling. That was the work of group of Yegor Babayev. So it's in reasonable agreement with our experimental data. So now I will switch subject, and you know, some interesting discoveries are made by accident. So you don't have intentions to observe something, and suddenly something pops up, and you don't know what to do with it. So bad students normally are hiding these experimental data from their supervisors, but good students are on the opposite. They are eager to discuss it with their supervisor, and then something is coming out. All right, so this will be about generation of vortex dipoles, generated if Meissner current flows around some spurious pinning centers or artificial pinning centers, which you can make by lithography. It doesn't matter in this case, but what does matter is actually you need some pinning sites, and you send through that area with pinning sites very strong Meissner current. So what happens then? So then you scan with scanning hole probe microscope this area, and then first you see nothing, so this is a Meissner state, and then suddenly you see this stuff. So which consists always from these blue, red. So blue means enhanced field, red means weaker field. So basically here you have maximum and minimum together. So you have some sort of dipole. And then first question you address is what is orientation of these dipoles with respect to the shielding Meissner current. So this is squid, not squid specific. No, this is scanning probe. Scanning hole probe. So you measure directly. Sorry? This is lead. Yeah, it's lead, but also we tried lead tungsten, not lead tungsten, but mostly this is on lead, thin film, type 2 superconductor. So now we want to understand what's going on. What are these dipoles? And actually, surprisingly, the explanation is quite nice and quite simple. Suppose you have here defect or pinning center, and you send through this area a quite strong supercurrent. In our case, it was Meissner current. And then, of course, current cannot penetrate insulating pinning center, and then it bends here like that, and you have half of the orbit which is clockwise, and here the supercurrent is repelled, and it goes like that, counterclockwise. So then, if you have clockwise half loop with current, and you have a counterclockwise current loop, then they generate positive and negative field. And the centers of these fields, actually, are located inside this defect. So, which means that actually it's impossible to make a closed contour which embraces only one object, this or that. For example, if I take closed contour like that, then my object is outside of that contour. If I take it like that, then I have both positive and negative. And then if I take them, none. So either both of them in any contour or none. This is very interesting. And then if you do the simulation for that current distribution, you know current distribution, of course you can calculate local fields. And then you can also correlate the direction of these dipoles with the position of sample boundary. And then what you see, you have different positions here of these magnetic dipoles. And then, of course, you can now recover the whole picture like that. So, and these areas, this one corresponds to this location, this one corresponds to this one to that, and this one to this one. So it fits quite well, actually. But that was a sample with spurious pinning centers. So we did not introduce intentionally any pinning centers. And of course, the next step was, why don't we take very well nanostructured superconductor with positions of pinning centers extremely well defined. So this was theoretical simulation first of these local magnetic fields, but to see it better, here we also depin these vortices from the pinning side. So this is the order parameter, and this is the local field. So this is bound vortex-antivortex dipole. First it's very pale, and we will see soon why. And then it becomes one flux quantum, and then it gets depinned. So again, it's very weak, pinned here, and then it's getting depinned. But you can clearly see, while being localized, it's less strong than was one flux quantum. And you might think that it's a little bit in contradiction with fluxoid quantization of superconductors, but not at all, because again, we are coming to this picture. I repeat, there is no way to make a closed contour enclosing only one object, either blue one or red one. It's either none, loop like that, or both of them loop like that, okay? All right, so that's simulation actually shows these objects like this red and blue, and it's showing up in the Meissner belt here, so in agreement with our experimental data. Knowing that, of course, and by the way, you can have similar effects if you bind the vortices with magnetic dot in plane magnetized. Then you still see these things pinned to the dot, magnetic dot, and then they are getting depinned if you send current. But that's a little bit too far from the main subject of this part of my talk. Okay. So conclusion for that, bound vortex dipoles can be generated when supercurrent, in our case Meissner current, flows through the area around pinning centers. Knowing that, of course, what you can do now, you can make now, okay. I'll come to this one a little bit later, so just, and then I jump to, once again, where I am. Ah, no. No. Back. Yeah, okay. So, important point here is that you have a spontaneously formed pinning centers, and then if Meissner current flows around these centers, you create these dipoles, which are visualized by scanning whole probe microscopy, and they have actually correlation with their position with the position of the circulating Meissner current. Important point also is that actually you can know in local magnetic fields, you measure with scanning whole cross exactly the amplitude of the field. You can see that these vortex and antivortex, each of them is carrying flux substantially less than one flux quantum. And I repeat, there is no contradiction here with the fluxoid quantization, because any closed contour embracing the pinning center encloses both vortex and antivortex in this dipole, and it's plus something minus exactly the same, and then this is 0, and 0 is also integer. And if you have a closed loop outside here, then none of them is enclosed by that loop. Okay.
Sorry, is it false that your order parameter drops exactly to 0 somewhere? So how strong is the pinning center?
We will come, that's why I wanted to jump immediately to that part where we have complete perforation of the film. So where we have very strong pinning centers and we know the position exactly of all pinning centers. Then we have no doubt. That was just the explanation how we found these objects. Okay, now I will explain first what you can do, what else you can do with the vortices and how you can visualize them if you use assembly of different vortex states. And actually, vortex matter has been studied by many groups in different locations in Europe and in the world. And many different techniques were used, like here by Auslander with co-authors, you use MFM tip, and you can use that to manipulate